Okay, this is lesson 9 from our probability unit. You can see we're going back to probability. Today we're going to talk about compound probability. So it says I can determine if two events are mutually exclusive. That's important because that will depend on how we calculate the probability. And then of course I can compute the probability of a compound event. All right, so this is going to take us back to our work with Venn diagrams, what we did in lesson 8. The general probability of two events. So if I want the probability of event A happening or event B happening, that's the same as saying, well, let's find the probability that event A happens. Let's find the probability that event B happens. But then we don't want to count some of those probabilities twice. So much like we have in the Venn diagram, we're going to subtract the probability that both A and B occur because we've counted it twice. We've counted it in calculating the probability of A, and we've calculated it in calculating the probability of B. So because we count it twice, we remove the probability that both A and B occur. Mutually exclusive, we're talking about, if you think of it in terms of a Venn diagram, we're talking about those sets, A and B. Mutually exclusive meaning there is no intersection, there is no overlap. So we would not have to worry about this at all. So if events are mutually exclusive, they don't have an intersection. They don't have cases where they're both true. So the probability of A or B is much simpler. We just do the probability of A plus the probability of B. We don't have to worry about that. Okay? All right, so in example 1, it gives us some probabilities of A or B, of A and B. We don't know the probability of B. The first question says, are the two events mutually exclusive? Well, we know that if there is some intersection, right, they're not going to be mutually exclusive. The intersection is represented by the probability of A and B. You can see you have that right here. That's a number. So because of that, this mutually exclusive is a no, right? Because we have an intersection, we have an overlap. So let's use our formula above. Probability of A or B equals the probability of A plus the probability of B minus the probability of A and B. Let's fill in what I know. A or B is 5/6. The probability of A is 3/4. I don't know the probability of B, and I know A and B is 1/4. So that's 5/6 equals 3/4 minus 1/4 is 2/4, which is a half. If I subtract a half is 3 out of 6, so 5/6 minus 3/6 is 2/6, which is 1/3. There's my other answer. Part B, same idea. Are the events mutually exclusive? I don't think I can answer that yet because I don't know what this is. So it's all tied to, does this have a value? If this is 0, then they would be mutually exclusive. So let's again use our formula. Probability of A or B is probability of A plus probability of B minus probability of A and B. So we know this is 0.5. This is 0.4 plus probability of B, 0.35 minus probability of A and B. So that's 0.5 equals 0.75 plus the probability of A and B. I'm sorry, not plus. That should be a minus right here I had. So if I solve, that means the probability of A and B is going to come out to be 0.25. So since that has a value, are they mutually exclusive? So I'm going to say no, they are not mutually exclusive because this has a value. All right, let's switch gears to a deck of cards. It says a card is randomly selected from a standard deck of cards. What is the probability that is an ace or a face card? So let's write down probability of ace or a face card. So let's think about which one of those formulas. Do we need the general, or can we use the mutually exclusive? So what we need to determine to figure out whether they're mutually exclusive is there any overlap? Is there a possibility that an ace could also be a face card? Well, hopefully you realize that's a no. Face cards are jacks, queens, or kings, and none of those could be ace cards. So in this case, that means they are mutually exclusive, right? So I can just consider this formula, which is the probability that it's an ace plus the probability that it's a face card. The probability that it's an ace. Well, there are 52 cards in the deck. That's my total number. There are 4 aces. Plus probability that it's a face card. Well, there are 52 cards in the deck. Don't forget, face cards are jacks, queens, and kings. But now there aren't just 3, because there would be a jack, queen, and king of clubs, spades, hearts, and diamonds. So that's a total of 12 face cards. So that is 16 out of 52, which reduces to 4 out of 13 would be my probability. All right, so similarly, card is selected. What's the probability that it's a heart or a face card? So let's write that down. Probability of a heart or a face card. So the question is, first, are these mutually exclusive? Right? Are they 2 separate sets, or is there overlap between hearts and face cards? Hopefully you realize there is overlap, because we do have hearts that are face cards. We have a jack of hearts, a queen of hearts, and a king of hearts. So there is definitely overlap, so it's not mutually exclusive. So when I set up my formula, probability of a heart plus probability of a face card minus probability of a heart or a face card. Okay, so I know probability of a heart. Well, there are 52 cards in the deck. There are 13 hearts. Remember, it's one of the 4 suits. Plus probability that it's a face card. We just talked about face cards up here. Remember, face cards are jack, queen, and king, and they are in each suit. So there are 3 in the 4 suits. That means there are 12 face cards, minus the probability that it's a heart or a face card. Not or. What should this have been? This should have been and, right? Probability of heart and a face card, because we're talking about the intersection. Sorry about that. So how many hearts are face cards? Well, we would have the jack of hearts, the queen of hearts, and the king of hearts. Those are both a heart and a face card. So there are 3 of those that we would have counted twice. We would have counted them in the hearts category. We would have counted them in the face card category. So we remove the doubles. If you simplify that, that comes out to be 22 out of 52, which reduces to 11 out of 26. Okay, again, that was supposed to be an and. That's the overlap. Okay, example 4. In a survey, 6 out of 15 took French, so the probability of speaking French would be 6/15. 11 out of 15 took math, so the probability that you took math was 11 out of 15. And 14 out of 15 took French or math. So what is the probability that a student took both French and math? So let's set it up. Probability of French or math, you can look above at your formula, equals the probability of French plus the probability of math minus the overlap, which we counted twice, so that's the probability of French and math. So let's see what we know. 6 out of 15 took French, so let's put that in here. 11 out of 15 took math, so there's the probability of math. 14 out of 15 took French or math, so that's here on the left. That's the 14 out of 15. What is the probability that the student took both French and math? So we're looking for this overlap, so I'll call that X for the moment. So if we solve that, we'd get, I'm going to come over here, 14 out of 15 equals, well, 6 and 11 is 17 out of 15. Minus X, and if you solve, you get X to be 3 out of 15, which is 1/5. So that would be the probability that a student took both French and math. All right, last example. It's very similar. A pet store has 25 green birds, 12 male, 13 female, 33 blue birds, 19 male, 14 female. You randomly select a bird. What is the probability that it's male or green? So write down your formula right away. Probability of male or green. So that would be probability of male plus probability of green, and there is overlap. We do have male green birds, so minus the probability that it's male and green. Okay, so we're counting that piece that we counted twice, we're removing. All right, so we're looking for the probability that it's male or green. So I'm looking for this guy right here, X. So what's the probability that it's male, right? Well, how many total birds are there? There's 25 green and there's 33 blue. So that's a total of what? 58 birds? And of those 58, how many are male? I've got 12 here and 19 here, so that's 31 male birds. So a little bit more work to calculate the probabilities here. Probability that it's a green bird. Well, my bottom number is still 58. There are still 58 birds. How many of them are green? That's right here, right? It said there are 25 green birds. So let's put 25 up there. Minus, all right, I'm still working out of 58 birds. Of those 58 birds, how many are male and green? So let's look over here. Of the 25 green birds, that's what we're considering here, we only want the male ones, male and green. So of these males, it said 12 were male and green. So that would be 12 out of 58. All right, so if we compute that, we get 31 plus 25 is 56 out of 58 minus 12 out of 58 is going to be what? 44 out of 58, which reduces to 22 out of 29. That would be the probability that it's male or green.